we are going to have a very quick tutorial on how to use openEMS, a free electromagnetic simulator. Here you have Octave window. I think if you're interested in openEMS, you already downloaded Octave and openEMS, installed them. And we will start by creating a very simple example, but this example also will be very useful for making your own projects. Okay, we will start by initializing C6 3D CAD data structure. C6 init 6. Okay, so you may wonder where does this function comes from. If we go to openEMS directory, include openEMS, openEMS MATLAB directory, and find this file init CS6, you will see the definition of this function and how it works. Everything is explained in this directory. You can find this functions are defined. Make an important one. Functions are defined in this directory. And why it's called MATLAB? Because openEMS functions are defined in. We can use Octave or MATLAB. That's why this directory is called MATLAB, because we can either use a free software called Octave or MATLAB. So we write code and press run, save and run button, and can check command window. If we write some wrong command and run it, then in the command window you will have an error, undefined line 8. So at line 8 we have some bogus symbols, so there is an error. So where I am learned from this, I just looked through examples. I learned from this examples directory. You can see there are antennas, optimizer, other transmission lines, and also tutorials directory in openEMS. So you can, let me note this. You can learn from examples and so we can use. Okay, next thing we need to do is to define materials. So what's define materials? Like this metal. C6 my line. This will are my material for microstrip line. And this function add metal, you can always find it and how to use it. As you can see, here's an example already. You can actually, this is the source code of scripts and documentation, kind of self-documented scripts. Next we will need my ground plane material, ground plane material. You can always press run and check if there's no errors. We clear this run, no errors. Continue. What also we need to add, and substrate, but also microstrip line metal. We will call it metal, ground plane metal, and this is substrate material. And also metal can be called material, but we just. And the next function is set material property. C6 my substrate epsilon 0.8 director constant. It's a director constant for our substrate. And you can find this function in openEMS scripts directory. You see there is a definition, C6 name and variables. We entered epsilon parameter, which is relative electric permittivity, so we can set more parameters if we need. Next, so we added defined materials. Next, we need to define geometry. Let's start simple. C6 add box C6 my substrate. We add geometry which uses this material, uses this defined material with epsilon 4.8, because this name and this name are the same. We're not using line or ground. My substrate priority 0, start and stop coordinates, and that's all. Our substrate will start minus 10, minus 20, minus 1, and then 20, 0. Okay, what's this? Right, C6 name priority 0 priority and one and x2 y2 z2 two coordinates, start and stop coordinates. So why we have -1 here is because our substrate thickness is 1 millimeter. Yes, you can also find this at box documentation. We added C6 property name priority start and stop coordinates. Here's an example in the M script, and our substrate width is 20 millimeter and substrate length is 40 millimeter, and because we have negative coordinates and positive coordinates because it's centered XYZ axis. What's next? Next, we add more information later. Now we just want to look how it looks like. Do we have any errors? First, we need to slice 3D space using two-dimensional planes through shape edges added with box function. We need to slice our two-dimensional space. Mesh, detect edges. We will try to run it. We don't have any errors now. And detect edges function is described here. You can see we used simplest syntax. What's next? Detect edges, sliced, define rectangular grid. C6 define rect grid. C6 mesh. Yes. So what's going on here is mesh was filled with coordinates in millimeters. We use delta unit to convert these to meters, because if the calculations use meters, everything is in meters measured, so we define a rectangular grid. It's okay, no errors. Define rectangular grid, and let's save this file, save these parameters to the file which can be understood by openEMS. We make a directory called temp, and we're saving this save data file that can be used by openEMS exe. by openEMS end this one and up the 6 cuts. Make temporary directory. Write openEMS temp test XML. Okay, but we also need FDTD. I haven't created. We need temporary make some FDTD. Set FDTD parameters, because this write openEMS, we see it needs FDTD structure, but we only have CS6 structure. So FDTD, our center frequency will be 4.8, center frequency, corner frequency, so it's like plus minus TT, need FDTD. This documentation, we use the simplest one, and criteria, out 6 side, FDTD, F0FC, and FDTD, set boundary condition, see everything is inside, FDTD, 8 sides, up, down, left, right, 1, 2, 3, 4, 6, 6, not 8. 1, 2, 3, 4, 5, 6. And there are also other kind. We use this because this is faster than PML. Try to run it, see if there are any errors. Error at line 42, because we haven't finished this yet. Right, openEMS, FDTD, and 6. Try to run this. No errors. Yes, no errors. Directory exists. Yes, this directory exists, but it doesn't matter. This is not an error. And display 3D model using the 6 cut plot. We will try if it works. No primitives. My line. Okay, because I have no primitives. Okay, something is wrong. So, okay, it's actually, we have primitives. As you can see, we have primitives for substrate, but doesn't have for line and ground. We will add this later. So this is actually our, this is our substrate. Yes, this is our substrate, and you can see if we make it rectangular and run this again. Okay, now it's rectangle and -10. This is was square, and now it's rectangle, which dimensions from 0, -10, +10, -20, +20. Okay, for example, you can make thicker substrate, very thick, 4 mm substrate. Run this, and now we have very thick substrate. It's a very thick substrate. Okay, next, let's go add more information. Next thing we will add is line, microstrip line. Width is around 3.6. No, width is around 1.8. So at 5.8 gigahertz, 50 microstrip line width is around on a thick substrate with ER equal. So with X coordinate 1.8, 1.8 divided by 2 because it's centered. Y coordinate is the same as for substrate because this length is equal to substrate. We still use -1 millimeter substrate thickness, and both coordinates will be equal. So Z1 equals to Z2 because it's 0 thickness. Strip line, it's like kind of ideal line, and we need to change this to my line. Check. Okay, now only ground have an error. So you can see we have more things. We have line and substrate. Next thing we need to add is to add two lumped ports. Two lumped ports. Okay, where you can find how to write this syntax in the examples, and this directory, for example, I will show you. You can see there are several examples, waveguide, how to add multiple ports, port 1, port 2, define multiple ports. You can find this in tutorials and examples directories. Port, add lumped port, add port. There's a description. 150 ohm. Coordinates, direction, start, stop, direction. Start, stop, direction, excitation, true. Because first we will have excitation at first port. Coordinates, first coordinate the same as microstrip line. Second coordinate the same as microstrip line. But this is at the closest edge of microstrip, and position will go from -1 from substrate thickness to 0, and direction in 0 direction. Yes, we will clear this, see if there's any errors, run it, no primitives. Oh, we have, you can see we have lumped port. Next, add second lumped port. It will be at the opposite edge of the substrate, and the only difference is that there is no excitation and it's second port. Run. We have some errors. Lumped element already exists. Okay, because port number is wrong, this will be second. We will clear this and start. My ground is not ready yet. Okay, now I have two ports. This fitting port and termination port, both 50 ohms. Let's add ground. Ground should be added here. C6, add box. We actually reuse this. Reuse this code, my ground. And the dimensions will be the same as substrate. Let's move it upper to the substrate. These comments, I think we don't need this already. Substrate coordinates of the ground, the same as substrate, but it will be at the -1. So will be have Z1 equals to Z2, 0 thickness, ideal ground plane, substrate ground, try to write. Now we don't have error, and now we have elements such as line, ground, substrate, and these ports, excitation, and this excitation to port, excitation, and ground plane, microstrip line, and substrate. Okay, we are very close to start a simulation. What else do we have here? Okay, let's think. We made initialization, define geometry using define materials, property of this substrate, define geometry, added this added 2 lamped boards, sliced our mesh, sliced 3D space for FDTD. This function will use these coordinates and these coordinates, and it will draw a 2-dimensional planes through this. Next we set FDTD parameters. What else? Define a rectangular grid, save data, and so what else do we need? What else do we need to make it work? We have lamped boards. Okay, we need empty space. This will be 6. Append mesh with surrounding empty space boundary coordinates. Appending principle. Okay, so appending principle. Assume that mesh X contains array, 3-element array. Then mesh x5 creates a new array. 1, 2, 3, 4, 5. 2 new elements. 4, 5. And we add mesh. We already have this mesh. Mesh x. Mesh x. 2 yz planes at. Okay, next mesh y. Mesh y. 2 xz planes and y. And vertical mesh C, you made a little smaller, xy planes at C minus 15 and plus 15. Check it out. You see, now we have empty space. Something to understand here. I just show you for clarification what this mesh is. It's simply this. You see these lines. These lines, this kind of 3-dimensional. It's a 3-dimensional array or FDTD. It's a 3-dimensional array. We just don't see it, which has elements with different size in space because it's one joint, second, third, and I just to illustrate, let's add some more coordinates at z plane. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and run. See what will happen. You see, we added this is 1, 2, 3, 4, 5, 6, 7, 8 in z direction. This mesh is actually, it's called a mesh, but actually it's simply coordinates of these planes that divide the space. Let's try to change it in x direction. Run and see. Now we have an x coordinate. It's an x-axis, and we have added. Now we delete this. We don't need these additional things, and see how it looks like. It looks okay. What's next? What else do we need here? This mesh is too low resolution. It's not enough to get correct results. So we need smooth pro mesh. Basically, subdivide the space by more 2-dimensional planes in such way that distance between adjacent planes is not larger than some value, and distance ratio between adjacent planes doesn't exceed. You will see what it means. Mesh, smooth mesh. We have this function here, description. You're gonna find all this. Find this smooth mesh. Mesh 0.51, and these things is, as you can see, mesh max res ratio. Mesh max res ratio. Mesh max res exceed ratio. Let's see how it looks now. As you can see, now we have much more denser mesh. And about this ratio, to illustrate, let's try to make our microstrip line very thin. Let's find where is our microstrip line. My line, let's put like 4.2, very thin line. How the mesh will look like. Parallel projection. You see, it's smooth. That's why this function is called smooth mesh. It uses this ratio. You can tune these parameters. Okay, let's make this back 1.8. Be almost ready for simulation. What else do we need? Right, openEMS 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 step. We just display this run FDTD, run openEMS, this function, run openEMS. You can find this function, how it works. All description is enough. Temp test XML, and we try to run this. Preview. We can comment this later. And look at command window, we can see that something started. Simulation started. Grab a cup of coffee or something else you can grab. Okay, simulation in, but you may wonder where are results. So here is how to run FDTD simulation. Process and display FDTD output, because openEMS generated the data. I will copy paste some things for beautiful. Is set font size, just for everything look better. Close all, close existing windows. From previous results we can close them. Space, linspace. You can find these functions Google online on Octave or MATLAB documentation. Linspace 200 points. Port, calc port. You can find this function in scripts. Port temp freak, and S11 will be equal to. Actually, you can find these things in examples. Let's copy paste. From another example. It's pretty straightforward. And finally, we need to display figure. Hold on. I will copy paste some things I prepared here. Hold on, create on, title, or put this without spaces. See if it works. Preview. Okay, we will waste some time because simulation will run the second time, but we also can comment openEMS simulation, so we will only display data and do not need to run simulation the second time to save some time, but now we just wait a little. Simulation, and as you can see we already have some results. Pretty good, yes. So what's next we can do? Let's add quarter wave stub. Actually, first I show how to display results without running simulation. We comment this out and comment this out. No need to preview. So this directly displays results. So let's add return here, so we only do preview, no simulation and no results, only preview, and it returns. Let's add quarter wave stub. We will add it here. Quarter wave stub. It starts at the right side of the X, Y, Z, at the right, at the bottom. Width will be the same. 0 is the top of the PCB. And we go to the right, for example, at 46.7. And we was here, it's below center of the line. We go up by half, 0. We do only preview. Let's look at preview. We added a quarter wave stub just to illustrate you. Make it longer, for example. Let's make it shorter. Like it's shorter, 1 millimeter. Run. You can see it's very short. So we let's try make very thin. 0.2, 0.2. Run. You can make very thin stub. Make it back, and let's rerun the simulation. First we let's save image from the previous simulation, how it worked, how it looked like. Need this, no need for simulation. First we look previous results, because we let's save this. This is previous result, octave, so previous result, and now we run simulation with a quarter wave stub. Now we have quarter wave stub. Open command window. FDTD started. FDTD started. It's going. It's our old results, and we okay. And here a new result, as you can see, because we added quarter wave stub, we have a very different picture. But that's not all. We can do more interesting stuff. I prepared some things for you. I prepared some more interesting things. How to display the data. Actually, I have prepared something. Define geometry, and here we add some more called field dump. In field dump, we save electromagnetic fields at the center of the substrate at minus 0.5 millimeters. And the next thing we add is thing that was shown in my UTMM course. I haven't seen anybody did this before with openEMS and Octave. So let's draw electromagnetic field distribution. It's my code that I developed. It's electromagnetic field distribution. What it does, it takes electromagnetic field dump, which was saved here. E field was saved, and we need to rerun this simulation. It will be much more interesting. Let's look. Wait a little. We have some error S1, but already we have some good things. As you can see, some distribution, but it's not very nice. 137, line 137. Scale. Scale. I did some error. So We do not need to rerun this simulation because of it. Just comment this and this, and just rerun. Okay, now it looks much better. You can see field distribution for a simulation.